Okay, these are the questions. Did the man put some sort of fuel on the fire on the nest before he lit it? Why is smoke white? Why do explosions happen? When it explodes, why does it make the shape it does? How much damage do they cause? And did people intend to make those explosions? Why is there a boom? And then someone also asked about making a nuke, a nuclear weapon. So let's go over some of these. What we saw last time is we saw this boom. Some of the descriptions were boom, explosion, fire, smoke. Here's examples of some of these. Some are huge, some are small. Here's Beirut, the explosion that happened this year. I mean, it demolished buildings. It just flattened things, you know. And so what's going on here? How do explosions happen? And so this one was accidental, and so was this one. The guy blew up his yard. And so why was he doing that? He was trying to get rid of cockroaches. So that was on purpose. He meant to blow it up, but he didn't mean it to be that big. And so roaches often nest under layers of decaying material. And so he was like, well, I'll get them where their nest is, and so I'll blow them up. And so what he did is he poured gasoline on it. And then he flicked a match, and it went boom. And when it went boom, it like blew the yard up, right? And so how did this happen? And so you have gasoline. Let's have gasoline be green. And so we have gasoline. And then we have a fuel source. How about this be, that's the world's worst candle. Maybe we can figure it. We have a candle. The candle's lit. We have fuel. We have gasoline. Gasoline is the fuel. The fire is the candle, and then we also have oxygen that's all out here. And so we'll just put O's for oxygen because that's all in the air. And so you need these three things. 1, 2, 3. Fire, fuel, oxygen. And then this equals fire or boom. So you need those three things. And so this is what gasoline looks like. If we look at the molecular structure of gasoline, this is what it looks like. And so it's all these C's and H's. That's pretty much all it is. There's an N right there. But pretty much it's all C's and H's. And so let's look at what those C's and H's are. The C and H represents an element. This is the periodic table of elements. Everything in the universe or in the world in the universe is made up of these things that we know of. These are the ones that we've figured out. And so you can make muscles with some things, you can make a phone with other things, you can make a computer with other things, but they're all come from these building blocks. And so here is the C, and here is the H. So we have a whole bunch of these together. Look at it again. There's the gasoline. A whole bunch of C's and a whole bunch of H's. And it tells you how many there are. Tells you how many there are because maybe the C will have 4 H's attached to it just like this. It might have 4 H's. Or it might be like this. So you have a bunch of C's together. And then you might have H's hanging off of them like this. But regardless, they're all C's and H's. So what happened exactly? And so if we have a C and a C and a C, and this is like you arrange these C's and H's in one particular way, like this. And then this is the fuel. We already established that this is gasoline. So then we spark this thing. We use a sparker, which is, let's change colors. Here's our candle. So we're going to add fuel to it, right? And then we have all this oxygen that's floating around out here. And what happens when you have a fire or when you have an explosion is that then these bonds start breaking. They break. These bonds break. Boom. Sometimes this happens really fast, like in an explosion. Sometimes it happens really slow, like when you're trying to light a soggy piece of wood at a campfire. It takes forever. you know. And so if it's wet wood, if the fuel is different, how it ignites will be different. And also the type of fuel source. If you try and start that soggy wood with a blowtorch, it's going to work much better than using those little teeny tiny matchsticks or something. So you can change the fuel and you can change the heat, but then you can also blow on it. And if you blow on fire, we all know what happens when you blow on fire in your wood stove. It starts to go faster because you've increased one of the three things: fuel, spark, and oxygen. And what happens is when you put those three together in the right combination, you start breaking these bonds. The faster the bond breaks, the bigger the boom is. And so when this thing explodes, why does it make the shape it does? Why does it boom, and why is smoke white? Well, if we look at this, we have C's, H's, and O's. We have a bunch of C's, H's, O's, H, C. We've broken all these bonds, so these guys are like flying everywhere. Woo! They're flying everywhere, right? And so they're flying everywhere. But then what do? These are like little bitty magnets, and so they want to stick back together. And so then what happens is the H's, two H's will combine with an O, which is an oxygen, and H2O is equal to water. So as the thing explodes, all these molecules are rearranging themselves in the form of water. And so a lot of the shape is, as the gas expands, a lot of it is just steam. And that's why it's white. And why does it go boom? If it accelerates fast enough, if that smoke expands, that smoke and steam goes out fast enough, it will go faster than the speed of sound. And when it goes faster than the speed of sound, it makes a boom. Haven't you seen those videos of the airplanes going really fast? And they break the sound barrier. They go faster than the speed of sound, and they go boom. And so that's what's happening, is the steam and smoke is expanding faster than the speed of sound and makes a loud boom. And then another question was, how much damage do they cause? Well, it depends on the fuel, the heat, the spark, and how much oxygen's in there. Fuel, heat, oxygen. Oxygen by itself will burn, like on an oxygen acetylene torch, like a cutting torch. That oxygen can explode. But you add these three things together, and you're going to go boom. And so how much damage do they cause? If you have the right kind of fuel, the right kind of heat, and the right kind of oxygen, you're going to have a space shuttle. Or if something messes up, the space shuttle could explode. If it's a different type of fuel, heat, and oxygen, it's going to go really, really slow, like wet wood. And so, did people intend to make those explosions happen? Some did, some didn't. The Beirut plant, they did not. They happened to have fuel, happened to have heat, and happened to have oxygen all in the right combination, and that whole thing went up and blew up. And so, yes, people will intend to. But like I was saying, you have to have the fuel, heat, and oxygen. And so to answer the question about the nuke, if you have something that's in a tight ball, and it's one of those elements from the periodic table, and it's uranium. If you have uranium, they might bind together, and it might be really, 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 really hard to break uranium apart from each other. It might be super duper hard. They could even have 3 bonds right there, and so they might just be so tight. And so the way you make a nuke is you have uranium, and then you have a shell that has explosives in it. These are explosives. And then if this shell is thick enough, when the dynamite, or when these black pieces explode, they will all have to explode inward. When they explode inward, that gives enough force to break these guys apart and then a really, 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 really big boom happens. So that's how you make a nuke. And so if we look at a whole different type of fuel, this is a fuel, this is this thing called ATP right here. ATP is made up of, each one of these little things is a C. So there's lots of C's, there's lots of N's, there's some O's and there's P's and there's H's, and all these are C's here too. You know, so there's lots of these elements, and they're all stuck together with bonds. And so this thing is a molecule right here. And so when this thing gets cleaved, when the bond breaks, look what happens. The bond goes from here to here just by losing one chunk of it. But when it loses that chunk, you get energy from the bond breaking, and there's our water friend. So you're getting water as a product also. So when Garrison's dunking a ball, or when I'm fishing or doing whatever, or writing, I'm using ATP as an energy source, and I'm breaking bonds, and my body's actually taking that energy and providing it to my muscles so my muscles can contract. So that is the end of the first one. Good day.